Imagine a time long before computers, a time of myth and legend. Even then, humanity dreamed of artificial beings. We told stories of machines that could think and act on their own. In ancient Greece, myths spoke of Hephaestus, the god of invention. He was said to have crafted golden robots to serve him. They were more than just statues, they were helpers with minds of their own. Across the world, in India, ancient texts described flying machines and mechanical soldiers. These weren't just fantasies, they were the first sparks of an idea that would one day change our world. They show a deep human desire to create life, to build something that reflects our own intelligence. This dream wasn't just confined to stories. Brilliant minds tried to make it real. Consider the incredible work of Al-Jazari, an inventor from the 12th century. He built amazing automated devices, or automata. He designed a peacock fountain with servants that would automatically offer soap and towels. He even created a musical band of robots that could play instruments to entertain guests. These weren't thinking machines in the way we understand AI today, but they were a giant leap forward. They showed that complex mechanical systems could perform tasks that seemed to require human-like control. It was a step from pure imagination toward physical engineering. Then came a crucial shift in thinking. The question became less about building a mechanical body and more about building a mechanical mind. This required a new language, a language of pure logic. In the 19th century, a mathematician named George Boole gave us just that. He created a system where statements could be either true or false, represented by ones and zeros. This is called Boolean logic, and it is the fundamental language of all modern computers. It allows complex ideas and decisions to be broken down into simple, binary choices. This was the key that would eventually unlock the door to machine intelligence. Before we could build a thinking machine, we needed a blueprint. The idea of a universal machine, one that could solve any computable problem, was born in the mind of Alan Turing. In the 1930s, he imagined a theoretical device, the Turing machine, that could read a long tape of symbols and follow a set of instructions. This wasn't a physical machine but a powerful concept. It proved that a single machine could, in principle, do the work of any other. His idea laid the groundwork for everything that was to come. It was the intellectual foundation upon which the entire digital world would be built. The pressures of global conflict often accelerate innovation. World War II was a turning point for computing. Alan Turing's theoretical ideas were put into practice in the most urgent way imaginable. He and his team at Bletchley Park worked tirelessly to break the German Enigma code. They built massive electromechanical machines like the Bombe to search for patterns in coded messages. These machines weren't thinking for themselves, but they were performing logical operations at a speed no human could match. This effort not only helped win the war, but also demonstrated the immense power of computation. It proved that machines could solve complex logical puzzles. At the same time, science fiction was planting the idea of AI firmly in the public imagination. Writers like Isaac Asimov explored what a future with intelligent robots might look like. His 3 laws of robotics offered a framework for how humans and intelligent machines could coexist safely. These stories were more than just entertainment. They made us ask big questions. What does it mean to be human? What are our responsibilities to our creations? Science fiction gave us a language and a set of scenarios to think about the social and ethical dimensions of AI long before the technology became a reality. The stage was set for the official birth of a new scientific field. In the summer of 1956, a group of brilliant scientists gathered for a workshop at Dartmouth College. It was here that computer scientist John McCarthy coined the term artificial intelligence. Their goal was ambitious. They believed that every aspect of learning or any other feature of intelligence could be so precisely described that a machine could be made to simulate it. They were filled with incredible optimism. They thought that a machine as intelligent as a human being was only a generation away. This event marked the beginning of AI as a formal discipline. Following the Dartmouth workshop, the first AI programs began to appear. These early programs, like the logic theorist and the general problem solver, tried to mimic human reasoning. They could solve algebra problems and prove mathematical theorems. It was an exciting time of rapid progress. Researchers believed they were on the verge of a major breakthrough. But the challenges were far greater than they anticipated. The real world is messy and complicated, and a machine's ability to reason about it was extremely limited. The initial burst of excitement soon faced the hard reality of computational limits, leading to a period of disappointment. The grand promises of the early days of AI were hard to keep. By the mid-1970s, progress had slowed to a crawl. Government funding agencies grew skeptical. They had poured millions into AI research with little to show for it in terms of practical applications. The machines of the time simply weren't powerful enough to handle the complexity needed for true intelligence. This led to a major cut in funding, a period that became known as the first AI winter. The dream wasn't dead, but it was forced into hibernation. Researchers had to scale back their ambitions and focus on smaller, more manageable problems. Out of this winter, a new approach emerged: expert systems. Instead of trying to create a general intelligence that could think like a human, researchers focused on creating systems with deep knowledge in a specific, narrow domain. Think of a computer program that could diagnose diseases as well as a doctor, or identify promising locations for mineral exploration. These systems were built on a set of if-then rules created by human experts. They were successful in many industries and brought AI back into the commercial world. It was a practical, if limited, form of artificial intelligence that proved its worth. However, expert systems had a fundamental flaw: they were brittle. They only knew what they were explicitly told. They couldn't learn from experience or adapt to new situations that weren't covered by their rules. Creating and maintaining these huge rule bases was also incredibly difficult and time-consuming. If a situation fell outside their programming, they failed completely. This limitation once again led to disillusionment. By the late 1980s, the excitement faded, and a second, shorter AI winter began. The field needed another new idea, a way for machines to learn on their own. That new idea was machine learning. Instead of programming rules by hand, we could create algorithms that allowed computers to learn patterns directly from data. This was a game changer. The focus shifted from logic to statistics. One of the most famous milestones of this era was in 1997, when IBM's chess computer, Deep Blue, defeated the world champion, Garry Kasparov. Deep Blue didn't think about chess in a human way. It used immense computing power to analyze millions of possible moves. It was a victory for a new kind of intelligence, one based on brute force calculation and pattern recognition from vast data sets. The true revolution began in the 21st century, powered by two key ingredients: massive amounts of data from the internet and vastly more powerful computers. This combination fueled the rise of deep learning, a type of machine learning that uses complex, multi-layered neural networks inspired by the human brain. Suddenly, AI could do things that were once thought impossible. It could recognize faces in photos, understand spoken commands, and translate languages in real time. This breakthrough wasn't just an improvement, it was a quantum leap that unlocked a new universe of possibilities for AI. This new power gave birth to generative AI. These are AI models that don't just analyze data but create something new. Models like ChatGPT can write essays, poems, and computer code. Others, like DALL-E and Mid-Journey, can generate breathtakingly realistic images from a simple text description. We are now in a conversation with our machines. We can ask them to create, to imagine, and to generate content that is often indistinguishable from human work. This has put powerful creative tools into the hands of millions and has started a new chapter in the human-machine partnership. Today, AI is no longer a futuristic dream. It is woven into the fabric of our daily lives. It recommends movies for us to watch, helps us navigate our cities, and powers the search engines we use to explore the world's information. In science, it's accelerating drug discovery and helping us understand the universe. In medicine, it's assisting doctors in diagnosing diseases earlier and more accurately. From agriculture to finance, AI is optimizing systems and creating efficiencies on a global scale. We are living in the age of AI, a period of transformation as profound as the industrial or digital revolutions before it. And yet we stand at a crossroads facing profound questions about our future. What happens when we create an intelligence far greater than our own, a superintelligence? How do we ensure that these powerful systems are used for good? The ethical challenges are immense. We must grapple with issues of bias in AI algorithms, the impact on jobs, and the potential for misuse. The epic journey of AI, from ancient myths to modern marvels, has brought us to this moment. Our task is not just to build smarter machines, but to build a wiser future with them. The next chapter is one we must write together, carefully and thoughtfully.